Okay, now this is a really awesome topic that I'm really excited for you guys to learn about. And that is that we can use our understanding of uh, geologic processes to reconstruct the past. Even though we weren't there to witness this and we can't make time machines to go back and look at it, we can figure it out knowing what we know about how rocks are formed, how they're deposited, and so on. So there's just a few rules that once we learn them, we can apply them to basically reconstruct the story of Earth's past, which is a really cool thing. It has lots of implications, you know, economically, environmentally. It's cool. Let's just get on it. Using rock layers to reconstruct the past. Okay, let's start off with this. If we want to know the actual age, like this rock is 17 million years old, to have what we call an absolute date, we have to use a technique called radiometric dating. And radiometric dating is something that we'll see in a minute can only be used on igneous rocks, rocks that form from melted, lavas and magmas. But the idea is this, and it's a pretty basic idea. It's very well vetted, and that is that every isotope in nature, and we know them all. We've made ones that weren't here, okay, and we know exactly what their half-lives are. In other words, like how much time does it take for half of it to decay from what the unstable isotope you started with, which we call the parent isotope, into the more stable, what we call daughter isotope. So basically, we can measure the ratio of parent to daughter and get a sense of how old a substance is. And the idea is this: every half-life, which is a time period duration, half of the remaining parent isotope will decay into the daughter isotope. So let's look at this example here. We have the yellow ones. Don't worry about the letters; they're inaccurate. But so basically, say we have an isotope that has a 1 billion year half-life. Okay, and there's plenty of them that have longer ones. All right, but here you go. So the yellow right now, when the magma cooled, and we had these minerals, you know what? 100% of the atoms in this one particular mineral were the yellow one, and it has a 1 billion year half-life. That means after 1 billion years of that crystal sitting there, half of these yellow ones will have decayed into the blue ones, into what we call the daughter isotope, slightly more stable. So right now it's 50-50. After another 1 billion years, which is another half-life, so every half-life, which is 1 billion years, half of the yellow ones are going to turn to blue ones. So now it's been another billion years. So half of these have decayed into blue ones. So now I've only got 25% of the original. So if we were to dig this up at this time and say, okay, look, we got this mineral, and we know that yellow decays into blue. All right, so we know that this one isotope turns into the other one, and we know that it must have started off 100% with the unstable one, the yellow one. But now we got 25% of it. That means there's been two half-lives, 50, 25, and we know each one took a billion years. So therefore, this rock is 2 billion years old. Another billion years goes by. Well, now instead of having 50% or 25%, I have 12.5%. So here I look at this one. I find the ratio of the parent isotope to the daughter isotope, and if it's 12.5, I know it's been 3 half-lives. And if I know the half-life is 1 billion years, then I know the rock is 3 billion years old. So that's how we do radiometric dating. And it's important to understand we can only do this with igneous rocks. And the reason is, otherwise we don't know, we might be able to tell how old the mineral is, but we just don't know like how long it's been a particular rock. But we know with an igneous rock, it started off as a mineral that had 100% of this kind of isotope, and then it decayed into this other one. Now, another way we can tell how old things are is by using fossils. So many sedimentary rocks have fossils in them. They're deposited in the water. There's things that live in the water. And so, the age of these fossils has been determined, over time by using, by using radiometric dating of igneous rocks to try to figure out how old these particular fossils are. But the point is, for every kind of fossil species that exists, we have a time range that we know that it lived. For instance, we know that, say, T-Rex lived from, let's just say, 85 million years ago to 65 million years ago. There's a time bracket in which this particular organism existed. So if I find a fossil here, and I know that this particular beautiful ammonite fossil lasted from 300 million years ago to 200 million years ago, then I know this rock is between 300 million and 200 million years old. It's a pretty basic idea. So fossils are a great way of determining the age of sedimentary rocks, whereas absolute ages are great for igneous rocks. So let's just look at how we would actually do this. Okay, so let's just say that fossil A lasted from this time frame. It first evolved 85 million years ago, and it went extinct 65 million years ago. So there's a 20 million year time bracket in which fossil A existed. Now let's say fossil B had a slightly longer one. It evolved 100 million years ago, and it went extinct 75 million years ago. So if I find a rock and all it has in it is fossil A, what I know about this layer is this layer must have been deposited sometime between 85 million years ago and 65 million years ago. But watch that. Okay, well, let's just go down here. Let's just say I look at rock B. This limestone here that has fossil B in it. Well, if all I see is fossil B, then I know this rock layer must have been deposited sometimes between 100 million years ago and 75 million years ago. But if I find this shale here has both of these fossils in it, then I know it must have been deposited during a time when they overlapped. So that means that it has to. It couldn't be any. It couldn't be any older than 85 million years because this one didn't exist yet, and it couldn't be any younger than 75 million years ago because this one went extinct then. So I know that this one right here had to have been deposited between 85 million years ago and 75 million years ago. And the point is, we actually find these assemblages of fossils in a lot of these rocks. So if you find a lot of different fossils, you can pretty well pinpoint the age of the sediment. So it's a pretty cool technique we have trying to figure out like when these different events. And remember, like a sandstone means it was a beach. Shale means it was offshore mud being deposited. Limestone means it was clear water reef. So we know when these situations were occurring in this particular locality. All right, so now let's look at a rule of geology here that's really straightforward, but many people haven't thought of it until it's pointed out to them. It's called the Law of Superposition. And basically all it means is this, that sediments have to be deposited on top of something, right? So if mud's going to settle down to the ocean and it has to land on something, so that something had to have been there first. So the idea is when I look at the rock layers, the oldest stuff is always on the bottom and the youngest stuff is always on the top, because in order for this shale to have been deposited, the mud that made up had to have landed on this limestone. Otherwise, where would this had to be there before this could be laid down. So when we look at rocks, we can always read them from oldest on the bottom to youngest on the top. It's kind of like if you got some, say, newspapers, and you read a newspaper and you set it on your table, and then a week later you got another newspaper and then you set it on top of that one, and a week later you got another newspaper and set it on top of that one. Well, the youngest newspaper is on the top of the pile, and as I go down into the pile, I'm going to find older and older and older newspapers. The youngest rocks are on the top, and as I go down, I get the older and older rocks. So we can tell what we call a relative age of them, just which one's older, which one's younger, by this law of superposition. So one of the things we often try to do in geology is try to understand how did the sea level change. So we tend to think the sea level is constant, but right now, because of global warming, sea level is coming up. It could come up like a lot, okay, maybe up 70 meters or so, right? Well, we know in the past there's been gigantic fluctuations, usually driven by either climate change, where you get when you get a lot of glaciers, that means a lot of water is drawn out of the ocean, so the sea level drops. And then when they melt, the sea level comes back up. Or also when the mid-ocean ridges are very active, they build up and they displace water and sea level goes up. And then when they're very, very, very inactive, they settle back down and the ocean comes. So we know that the sea level goes up and down throughout geologic record. So when we look at a rock layer, we're looking at one place on Earth and we can see what did the ocean do. So look here. In this region here, I see sandstone on the bottom. That's the oldest of these three rocks. Well, I know that means there was a beach there. So at this point, there was a beach. Then what happened was, after that, we have siltstone. Well, that means the water's got a little bit deeper, because remember, siltstone gets deposited a little bit offshore from where the waves are breaking. So I know that between this layer and this layer, the sea level must have gotten deeper, because it's quieter now, and that process kept going, because now I have even deeper water sediment. So just think of sandstone being very, very shallow, like shoreline environment. Siltstone slightly deeper, a little bit offshore. Shale, which is muds, considerably deeper. Pelagic sediments, really, really deep. Okay, so we can tell what happened, that the sea level basically was coming up in this time period, because where we're standing got deeper and deeper and deeper. I mean, isn't that cool that we can do that? Okay, there's another one. It's called another thing to know about. It's called the Law of Original Horizontality. Now that seems like a mouthful, but really all it means is this: that the sea level, the bottom of the ocean tends to be a flat surface. If it's tipped, then the sediments would just run down, right? And they pile. So basically, it's got to be flat for sediments to get deposited. So when sediments get deposited, they are essentially being deposited horizontally. So basically, with their surfaces perpendicular to the gravity force vector. So basically, when I see this, I know that is the position that they were originally put down in. So sedimentary rocks get laid down horizontally. They don't get laid down vertically or at weird angles. They get laid down horizontally. But they don't necessarily stay that way because tectonic forces, once they become rocks, can tip them and bend them and fold them. So what happens is, I know that these rocks A, B, and C, and we go deeper than that. Okay, D, E, F, whatever. They were laid down horizontally. So here's my youngest one. Here's my oldest one. But then sometime after they got deposited, tectonic forces tipped them up. And so I see it now, like when I see rocks like this, they did not get deposited that way. They got deposited horizontally, the law of original horizontality. But then what happened was afterwards, tectonic forces bent them. And so now what I see is, whoops, I get this back. And now I just see this part over here. Okay. Or maybe I see them completely folded up. Okay. Like this here. Well, I know that first there was D, then there was C, then there was B, then there was A, like this, horizontally. Afterwards, an event happened that caused it to fold, and because we never see rocks that get deposited this way. They don't. They get deposited this way. So we know that this folding event must have happened afterwards. So if I know rock A is 800 million years old, then I know that this folding event happened more recently than that. Then we have a thing called an unconformity. Now, an unconformity just basically means that there's a gap in the rock record, and this gap is there because, like if I look here, there's no gaps in this rock record, right? First there was C, then there was B, then there was A. First there was E, then there was D, then there was C, then there was B, then there was A, then it got tipped. But there's no missing information. However, what happens in an unconformity is there's missing information. That happened because the rocks must have gotten lifted up above sea level so that wind and rain and movement of glaciers tended to move rock material away. You weather it and erode it and carry it away. And then sea level came up or the land sank, either one. And then I got more sediments put on top of it. So what happened here was first there was G, then there was F, then there was E, then there was D, then there was C. Then there was a tipping event that tipped them all up out of their original horizontality. Then the whole thing got eroded down to here, forming what we call an unconformity. And then later the sea level came up or the land sank, and then B got deposited on that and A got deposited on top of that. So we can tell like when, between, if I know the age of B because of fossils and the age of C because of fossils, then I know when this event happened, when the land got exposed to erosion, when it was above sea level. And I see the same thing here with the folding event. So I know that this unconformity happened after this folding event, and then later on, rocks B and then A got deposited on top of that erosional surface. So let's just look at how I interpret this. Okay, so in this one above, here's what I've got. Okay, so rocks F, E, D, and C got deposited. Then there was a tectonic forces called it to be folded. So the folding event happened after C got deposited. Then the whole rock layers got lifted up above sea level, or sea level dropped, and then we eroded the surface of them, forming the unconformity. Then sea level rose again, and then B got deposited on top of that, and then A got deposited on top of that. All that information just by looking at these rocks. It's so awesome. All right, and then we have what we call cross-cutting relationships. So a cross-cutting relationship means that basically sometimes there's things that don't have anything to do with sedimentary rocks getting deposited, but breaks or intrusions of igneous rocks cutting through them. So when I have a cross-cutting relationship, what I know is the thing that cuts through the rocks must have happened after the rocks were there. Otherwise, there was nothing to cut through. So I know that this one has to be younger because it couldn't have cut through A, B, and C unless A, B, and C were already there. So when I look at this, I know that C got deposited first, and then B, and then A. And then after it, this igneous rock pushed through here. And igneous rocks, by the way, they're not deposited. They can intrude, so they don't follow that law of original horizontality because they're not settling out of the water. So the law of original horizontality only applies to sedimentary rocks. Cross-cutting also applies to faults. So let's just look at this. Okay, so first came C, then B, then A, then a folding event folded them. Then a crack in the rock happened, and there was sliding along it, so it became a fault. So this fault represents a cross-cutting relationship. So I know that this fault has to be younger than all those other things that came before it. I know it had to have come before the depositing of rocks D, C, B, and A. It had to have come before the folding event because the folding event was cross-cut. Okay, and then finally, the last thing is that we can also use cross-cutting with craters, like we see on the moon, or also here on Earth with volcanism or with meteorite impacts. So if I have two craters that overlap each other, then the younger one, which is complete, which is basically roughly circular, the one that is roughly circular and not disturbed must have happened afterwards. This one must have been here for this one to have altered its shape. Now, the other thing is, if I see one inside of another one, and we see this on the moon quite a bit, so it allows us to interpret the history of what happened on the moon. I can look, and I know that if there's one inside the other one, this one must be younger, because if this one had been here first, when this one formed, it would have obliterated this one. So I know this one must have formed, and then this one happened later, because this one changed this one, and not the other way around. Okay, so that's it. That's a lot of information, I know. We need to practice this some, so that's what we're going to do for the remainder of the class period. So good luck with this. I find this exciting stuff. I hope you enjoy it.